happy to be here, guys, talking about one of my favorite subjects, TypeScript. So the title of the talk is TypeScript JavaScript, the Snyder cut. So it's really all about the type programming aspects of TypeScript. So my name's Eamonn Boyle, as Adele says. I'm one of the trainers at Instill. Garth?
I'm another of the trainers at Instill. I've been doing this for far too many decades. Yeah.
He's my boss. I don't know where your window is, but he's my boss when I point that way. So my top tip whenever giving presentations is keep your pop culture references timely. So when we were thinking about this talk, Zack Snyder's re-release of Justice League was in the news. It was topical then. Nobody remembers it now. Nobody cares about it. But our thinking was, the Zack Snyder director's cut of it was a much better version of sort of the hacky, sort of thrown together Justice League original release. So we thought, that's a little bit like TypeScript. TypeScript is the much better version of JavaScript, but it's still fundamentally the same thing in that TypeScript is a superset of JavaScript. If we were taking a more timely pop culture reference, it might be this. Garth, contain yourself. Yes. Garth and I are big Dune fans, so we're fingers crossed on whether or not the new Muad'Dib is going to be better than the old Muad'Dib.
I am literally wearing the t-shirt, so yeah. Yes,
indeed. Excellent. So yeah, big Jude fans. So JavaScript is super popular. Something like over 13 million developers worldwide. By a lot of metrics, it's the number one programming language. So this is the Red Monk metric. It has TypeScript as number 8. This is the Stack Overflow one. Again, it has JavaScript as number 1. Interestingly, TypeScript is number 8. And TypeScript over the last number of years has just crept up higher and higher and higher because there's so many JavaScript developers. TypeScript being a superset makes it sort of a really sort of up choice sort of for this space. If you look at what languages are most loved, this is again a Stack Overflow survey. JavaScript's actually further down. It's number 10. TypeScript is number 2. People that use TypeScript, especially people are coming from JavaScript, they love to use TypeScript. Rust, interestingly enough, is number 1. We're not going to talk about Rust today. So yeah, TypeScript's loved by lots of metrics. This is the state of JavaScript. 72% of people have used TypeScript and would use it again. So they've made the transition. So what is it? It doesn't reinvent the wheel. It basically just gives us C in JavaScript. It adds static typing to the language. It is a pure superset of JavaScript. You could take the TypeScript compiler, throw it a pure JavaScript, and it would just be a really good static analysis engine. Brings you better tooling, better code validation, static analysis, error checking, all of that good stuff. And at this stage, really, really well established, as you can see from those tables, and very, very stable. Okay, so good engineering, doesn't reinvent the wheel, improves upon the wheel. Okay, now there's lots to talk about when it comes to TypeScript. We're not going to cover all of that today. We're just going to go a glancing pass through the type programming aspects of it. So we're going to look at some of the more advanced type features like unions, intersections, map types, and these kinds of things. And we're going to try and show that these are things that everybody will want to use in their code. You'll benefit from them in libraries, but you'll want to integrate them into your own code because they're so great for removing redundancy. So this is not only for like Haskell and category 3 geeks and stuff like that. The main takeaway I want you to come away with this talk is this is practical and this is useful for everybody. And it's all about removing redundancy in your code. So I had to get a DC reference in. So, that's removing redundancy. I had to get a second DC reference in. So there is no redundancy in Jason Momoa's abs. Jason Momoa's abs are a perfect analogy for type programming. Adele, that's the slide I thought that you might like. So as we go through here, we're going to be looking at code like this. This is how you actually do some of the more advanced type programming bits and pieces. This is not really what I want you to focus on. We're in half an hour. We're not going to be able to explain all of this. You'll not come away understanding all of this stuff. We'll talk about it, but it's really just to get to this bit. The whole point is remove redundancy and create simple, elegant code. And to make it easier, I'm going to put a little Jason Momoa's abs beside the bits that you need to focus on. Okay? So over to you, Garth.
Very good. So the first thing that TypeScript does is it adds static typing to JavaScript. So we're all familiar with the static versus dynamic typing debate, and you could spend days just talking about that. We're not going to. But static typing can be broken down two ways. There's the kind that you're already used to, and that's nominal typing. So nominal typing is when a type is identified by its name, and that's it. So if two types had exactly the same structure but different names, too bad, they're different types. Yeah. Structural typing, as the name suggests, is all based around structure. So if two types have the same internal structure, the same fields, methods, members, whatever you want to call them, then they're regarded as being equivalent. Now, for those of you who have done Python, you'll be familiar with duck typing. This is a very similar concept. Yeah, two objects get treated the same at runtime if they have the same internals. Yeah, but what we're talking about here is something that happens at compile time. You know, something that gets enforced by the TypeScript compiler. So let's look at a little example. Let's say we've got three types: movie, policy, and request. So from a nominal typing perspective, the kind of typing that you're used to, these are completely different types. You know, they have absolutely nothing in common. They're disparate types. Yeah. From the perspective of structural typing, these are almost disparate types. Yeah. But they do have one thing in common. They all have a property called ID. So in the case of movie and policy, ID is of type number. In the case of request, it's of type string. So there is a little bit of overlap in the structure. If you kind of imagine a Venn diagram, there is a little bit of overlap between the three types, and this is something that we can exploit. So what we can do in TypeScript so let's say that what we want to do, give you the use case first. So what we want to do is, let's say we've got arrays of the three types. So we've got arrays of policies, arrays of requests, and arrays of movies, and we want to find things by ID. So if we're going to use the JavaScript find function, we have to specify a predicate. You know, we have to specify a function that takes an item and returns true or false. And we can write a higher order function, you know, a function that builds and returns a function. So what can we do with regular nominative typing? Well, if we were doing it that way, then we'd need three separate functions, because we'd need three separate lambdas. Yeah, we'd need to have a function that returned a lambda that took a movie, yeah, and decided if the ID of the movie was equal to the supplied ID. We'd need a function that returned a lambda that took a policy and checked if the ID of the policy was equal to the supplied ID. We'd need a function that returned a lambda and took a request and checked if the supplied ID was equal to the ID of the request. So note that the structure of the code is the same in each case, but because we're doing nominative typing, you know, in the C# or Java or whatever implementation, we would need three versions of the function. But what can we do in TypeScript? Well, we can define a structure, a type, you know, let's call it ID type. So we're saying something is of shape ID type if it has a property called ID, which is of type number. And then we can write a function called hasID that returns a lambda that takes an ID type and returns a Boolean. And the good thing is that we can now use this for both movies and policies. We can't use it for requests, because remember, in request, the ID was of type string. Yeah, but we can use it for movies and we can use it for policies. You know, so already structural typing has helped us along. But structural typing is even more powerful whenever you combine it with generics. So you see here, we can define our ID of t, which takes a type parameter of t. So now the property called ID is of type t. So we can create a function called hasID that takes advantage of both structural typing and generics, you know, and type parameters. So now anything that has the shape of having a property called ID, which can be of a generic type, that's now within reach of this function, if you like. Yeah. So now the one function hasID that will work for movies, policies, and requests. So that's the Momoa's abs. You know, think about the amount of duplication that we can strip away there because we have the structural typing, you know, so very, very powerful. So then on top of the structural typing, we can build on algebraic types, as people like to call them these days, you know, and that sounds scary because that might involve math, okay, but it's not really that frightening, yeah. So it's just the ability to do ors and ands in your code. So the union types, as they're called, these are used for saying, look, we have a type A and it can be a B or a C or a D. So you see here, we're defining a type called primitive, and we're saying this could be a string, or it could be a number, or it could be a Boolean. And the reason why TypeScript needs this is because it's sitting on top of JavaScript. And in JavaScript, the convention is that you have functions that can return multiple types. You can go all the way back to jQuery or something like that. So it's always been the case in JavaScript that it's considered fine to write a function which can return values of different types. So we need this kind of thing here. However you choose to lay it out. People like to do it different ways. So here's some real world examples. Here's one from the React library. Okay, so you see we've got an interface, and we're saying this interface has an optional property called max, which can be a number or a string. It is an optional property called min, which can be a number or a string. It is an optional property called value, which can be a string or a read-only array of strings or a number. So that this can be very useful for imposing some kind of strong type structure on top of what JavaScript is already doing. And then here's an example from Angular, and this is a more tricky one, but you see we've got a function called canActivate, and you see the type that it's returning there, it's been laid out onto 3 different rows. And what we're really saying is, look, this can give you the results synchronously. So depending on what you pass in, this could return a Boolean or a URL tree. Or it could do it asynchronously and return either a Boolean or a URL tree within a promise, or it could do it asynchronously again, but this time use an observable, a reactive stream, whatever you want to call it. So that you can get an observable of Boolean or URL tree, a promise of Boolean or URL tree, or a Boolean or URL tree, and there's 3 separate cases there, 2 asynchronous, 1 synchronous. So let's say we needed to use that in our code. So let's say we called that function and that had returned a result, and we want to take that result and pass it into some other function. Well, here's what it might look like, yeah? And as you can see, the range of types that result might have is fairly formidable. And inside the braces there are a list of the functions that we would want to call, but we're not going to be allowed to call any of them, because only in the case where it's a URL tree would we be allowed to call query params. Only in the case where it's a promise would we be allowed to call them. Only in the case where it's an observable would we be allowed to call subscribe. So because the compiler can't know for sure what it is, we won't be allowed to call any of those functions. So what we need to do, and the IntelliSense will therefore be crap. So what do we need to do? Well, we need to test the type of the thing. So in JavaScript, there are many different ways that you could test the type of the thing. You could use type of, you could use in to check if an object contains a particular property. You can use instance of, and so on. So we can test the type of the thing. And then what we'd have to do in other languages is we'd have to convert the variable to the appropriate type. So let's say we detect that result contains a property called query params. Well, then we can create a new variable URL tree, and we can say that should be result as URL tree. So in other languages, what we'd have to do is we'd have to say, we now know this is really a foo, so we need to cast or convert it to a foo. But the really cool thing is you don't have to do that in TypeScript. So here's the same code, but now written using proper TypeScript. So the TypeScript compiler is smart enough to work out that if you've said type of result is Boolean, then it's a Boolean, and you can do Boolean things with result. Or if you've said query params and result and that returns true, then it's a URL tree, so you'll be allowed to access the query params. Or if instance of promise returns true, then it's a promise, so you'll be able to attach a callback to it within. And then finally, if it's none of the above, it must be an observable, so we'll be allowed to subscribe to it. So you see there, the compiler is doing an awful lot of work on your behalf. It's inferring what the actual type must be, and it's converting the variable for you behind the scenes, and all of that just happens as if by magic, so that's brilliant. Of course, that code might be a little bit long-winded. You don't want to have lots of calls to instance of and so on cluttering up your code. So what you can do is you can put that in what are called guard functions. So a guard function is just a function that takes a parameter and returns true if that parameter is of a particular type. And the TypeScript compiler will make use of those functions. Okay, so you see here, if we'd written the function is URL tree, well, then we can say else if is URL tree result, result. And if that returns true, well, inside the braces for that if block, well, then result will be treated as a URL tree. So we'll be able to access the query params, so that's really cool. So let's look at how you would declare that. So the declaration is pretty much what you would expect, except that you would think that it would return a Boolean. And it does. This function does return true or false. But you see there, instead of the type Boolean, we've said result is URL tree. So what the first time I saw this, it really threw me for a loop. Yeah, but what this baffling little bit of syntax is saying is this function will return true if the parameter that was called result is actually a URL tree. So if the parameter called result is a URL tree, that's what this function returns. So that enables the TypeScript compiler to say, aha, I know how I can use this now. Very good. And then they've continued improving it. So here's a nice new feature in 4.4. So this is something that wouldn't have worked before. So let's say what we do is we do a test. So let's say in some way we work out whether or not the parameter called result is actually a URL tree object, and if it is, we set the variable is URL tree to be true. Okay. Well, TypeScript can work out what we've done. So later on, we will be able to say if is URL tree, and if that returns true, then we'll be allowed to access the query params, So we can do the test. We can work out what the type of the input is. We can store that in a const variable, and then we can use the variable later. So you've now got two ways of refactoring your code. You can put all the type tests and guard functions, or you can refactor them into constant variables, and put them somewhere where they're not going to get in the way. So once again, that's the Momoa's abs. It's really good. So you've got the union types, and then we also have intersection types. So if the union types are the or, these are the ands, okay? So here's an example. So we've got this type called props with children. So P is some type, and we're saying a props with children of P is it's everything that P is and also has an optional property called children, which is of type React node, okay? So we can use that if you like mix in an extra property called children into any particular type. So this is how we would use it here. A little bit of React code. We're creating something called task list, and this is a functional component. And we're saying that the properties of this component are given by the interface props. So for each component that we write, we come up with a little interface, basically to describe the data that this component needs to do its work. But what will happen is that the actual parameter there called props, that will be of type props with children props. So we say FC foo, but then the thing that actually gets passed in will be of type props with children foo, so the children property will have been mixed in. Okay.
Awesome. So other things we have available in TypeScript are literal types. So literal types are, again, very strange the first time that you see them. It's where we're basically taking a string or number, a Boolean, and thinking of it as a type. So value here has both the value 12, but we can explicitly say it has the type 12. So the only possible value is 12. This has some usage on its own, which we'll see, but where it comes in really, really useful is whenever we sort of combine them with the union types. So for example, here we have story points, which is one of these possible values, 1, 2, 3, 5, etc., or even the string infinity. Those are the only valid values for that type. So we can get sort of enforced error checking and tooling support, autocomplete, refactoring, navigation, all of these things with these constant values. And so this is sort of a really useful alternative to enums. So let's sort of see how we can use this. If we consider the standard JavaScript fetch function, in it, you pass in the URL and a configuration object. The configuration object says what kind of HTTP request you're going to be doing. So if we were saying that one of the things that you can specify is the method, so that can be put, get, post, etc. If we go and drill into those types, we'll find that the request init object that we're passed in here, the method property is an optional string. So it's just of type string. So we can pass in invalid values here, and we will find out at runtime that they were invalid. So could we improve this? We could create a string union, a literal type union of all of the valid methods, so get, post, put, etc. Okay, we could have defined our request init type, and in fact, I can create it here on the fly. Safer request init type as being the request init type intersected with a type that has that method property, but this time of type HTTP method. So now we're basically making that method property safer, and then we could define a safer fetch function that has that as the second parameter. So what happens when we do that? Well, the code looks pretty much the same. We're still passing in an object, we're still passing in a method, but now we're going to get error checking, and if we pass in invalid strings or accidentally type invalid strings, it's going to be a compiler error. Before we run the program, it's going to be a compiler error. The other thing is that we'll have awesome autocomplete, so much better developer experience as we're building this stuff. So this is definitely Momoa's abs country that we're in. Other things that we can do is we can extract these values automatically. So if you look at this here, we have an array with some objects inside it. These are chess pieces. Now, something to sort of note is that I'm marking this as const. And when I do that, the TypeScript compiler is able to say, okay, well, this data is constant. That means I can drill into this and extract some information. And the other thing you should notice is that I haven't actually done any typing here whatsoever. I haven't specified chess pieces types. I haven't specified what the type of name or worth is. I've just defined the data. So what this is all about is trying to create the data as the source of truth for other information that we can determine. So what we can do is we can ask the TypeScript compiler to look at that data and build us some new types. We can define the chess piece type, the piece type here, by saying, well, it's the type of the objects in that array. So we can basically say pieces number. That would give us the union of all of the types that are inside this array, which they're all the same. So that piece will now define our type. We can also drill into that and say, okay, well, what type is name? And it will be able to build us out a union of all of the possible values. So pawn, knight, bishop, etc. We can say piece worth and extract out the worth values. That's the union of all of the values inside there, 1, 3, 5, etc. And we can say piece shape and extract out the shapes. So I haven't defined those types originally, but I'm then able to construct the types from the data. The data is the source of truth. When the data changes, these types change. And that's what it's all about, removing that redundancy and having a single source of truth. And, whenever we're using this, of course, we'll have the same behavior as with the fetch call. We'll have really good autocomplete, really good error checking. This is all Momoa's abs. Okay. Other things we can use literals for, they're really good whenever we want to get the compiler to make a selection between multiple options. So for example, choosing between types and function calls. So consider this function here. This function creates a DOM object with a specific tag and then assigns it an ID. And what it's returning at the moment is an HTML element, okay? And this is fine, this works, but it is the abstract HTML element, so it doesn't have all of the specific behaviors of specific kinds of tags. So, inputs and divs and things like that will have different functionality that we'll be missing because we're only getting back the abstraction. So we can use literal types to get the compiler to figure out which call we're making. So we could do function overloads here. So here what I've got is multiple signatures for a single function. And the first parameter, although we can think about it as a string, we can also think about it as specific types, p, div, h1, input, and so on. And we can use the compiler to then figure out, okay, which one am I passing in, to then figure out what the return type should be. So each of these has a different return type, which means when we make the call and we pass in p, we get back a paragraph element. When we pass in div, we get a div element. So these are all going to be specific types, not the abstract form. And then the autocomplete development experience is going to be much better. So this is definitely another example of Momoa apps. We could have actually done this a different way. This is the way that create element actually works in the standard library. Here, what we've done on the bottom, we've created a type that's only going to be used for mapping in type space. So we've got a type here, which has a series of properties, and each of those properties has a type on the right-hand side. And we're not actually going to create an object of the shape. We're just going to use this object to do lookups in type space. So what we're saying here now is we're saying the type of tag is not p or div or string, it's k. And we're going to say that k must be one of the property names from our map. And that will then allow us to use that K to look up what it's pointing to, what its mapped type is. So this would give us the same behavior. And this is quite a common trick that we can use in TypeScript. But again, what we're trying to get out of it is just have the type specific calls and have that sort of specific types coming out. So we don't have to think so much about the implementation. We just want to have nice specific types and good autocomplete coming out the other end. The other thing that we can use literals for is discriminated unions. So discriminated unions are basically type unions, but there is some mechanism built into their structure that allows us to identify a type. Okay, so let's look at this example here. Typically with discriminated unions, the shapes of the objects are going to be different. So I've got three events here, a touch event, a mouse event, and a keyboard event. And you can see that the data inside these events is different. So a keyboard event would have a key and whether or not shift was down. A mouse event would have which button was pressed and the position on the screen that the click happened, for example. And we have all of these event types inside an event union. So when we get an event, it could be any one of these. But we have one additional property, kind, which is being assigned a literal type. Okay, so the type of kind is not string. The type of kind is either touch, mouse, or keyboard. So by having this literal type, the compiler can then use comparisons to this property to figure out information and help us. And again, this is what it's all about. It's not about doing sort of clever mathy category 3 stuff. It's about making our code safer and easier to write. So when I'm doing a switch on that event kind property, the tools can automatically see all the possible values and they can do an exhaustive case list for us. So I can just use the IDE to expand out the branches, and it does that automatically for me. Not only that, if I'm in one particular branch, say for example inside keyboard, if I do my autocomplete, it's going to know that it's a keyboard event because it's been able to determine it from the value comparison with kind that it must be this type of object. So we have key and alt key, etc. And of course, we'll have error checking. So if we try to do a touch type event inside here, that's not going to work. Okay, so this is definitely Momoa's abs again. We can also do mapped types. Map types now, again, map types are strange the first time you see them. They're a little bit like iterating, but at compile time in type space, okay? So what they allow us to do is create a new type from an old type, okay? This is the rough structure. This basically makes a copy of a type. So this is making a copy of T. And what we do is we define one line, like one property, key, and then type. But what it's actually going to do is iterate over to populate multiple key type pairs. Okay, so this thing here on the left hand side of the colon is defining all keys, and this thing on the right hand side is defining the type of all of the members with those keys. So what we're basically saying here is go through every member of T, K in key of T, and the type of that member in our new type is going to be whatever it was in T, TK. Okay, so this is basically just making a full copy of a type. And you can think about it a little bit like iteration at compile time. So if I had a type person with name, date of birth, and marriage status, I could make a new type, copy of person, and it would be equivalent to writing all of this. Okay, making a copy is not super useful. It becomes useful when we change our copy syntax to modify the keys and the types. So here is what read-only would do. This is actually a built-in one. Read-only is actually built in to the language, but this is how you write it. So this is basically adding the read-only modifier to each of our keys. So I can pass in any type T, and I'll get back a type that's the same, but all of the properties will be read-only. So it's equivalent to this type at the bottom, read-only person. But I can do it in one line, Momoa's abs. I can also do a optional modifier on the keys. So again, in one line, I can say a partial of some type, and that's equivalent to again, copying and pasting and writing the thing at the bottom. Definitely more Momoa's abs. This one is more complicated. What I'm doing is I'm not going through every K in key of T. I'm going through every P in K. So I'm passing the second generic parameter, which is the union of all of the members that I want. So I'm basically picking out from the object shape the bits that I want, but it will have the types from the original source object. So I can, again, create a new type, which only has name and date of birth with the correct types, and I can do it in one line. So that's definitely Momo's abs. All of this, why are we doing any of this? The reason why we're doing this is because we want to have a single source of truth. We don't want to have copy and pasted code, because when we have to change it, we've got to edit in all of those different places. If we have a single source of truth and then we have other types derived from it, when we make a change in that source of truth, all of the other types will update accordingly. The original type changes, the derived type changes. We're aiming for Momo's abs. That's what we're looking for. Here's an example function. This one is making a copy of an object and making some updates to that copy. So we pass in any object source and then an object, which is the partial of that type. Again, it's all generic. It's all T. It doesn't matter what I pass in here. Whatever I pass in as the first parameter will have to be a subset of that will have to be the second parameter. So this thing here is just creates it on the fly, the type. And whenever I pass in a person, well, I have to pass in a subset of person as a second parameter. If I passed in a different type, it would be a different subset. And this all just happens automatically. So this is all, again, Momo's abs. Garth?
Cool. Yep. So whenever you encounter map types for the first time, all the examples that you see are like one-to-one transformations. So you're told that the new type is the same as the original type, except everything's read-only. The new type is the same as the original type, except everything's optional. The new type is the same as the original type, except everything's a string. But what you can also do is you can use the ternary conditional operator, the question mark conditional. So you can say, okay, for some type T, if it extends from foo, then use A, otherwise use B. Okay, so you can make a decision of the type of the thing in the output type. So we have a source type, we have an output type, we're doing some kind of transformation. And as I say, up until now, it's always been a one-to-one mapping. But what you can do is you can say, okay, if a particular type extends from something, then use A, otherwise use B. Okay, so here's a little example here. We've got this thing called return type. Okay, so this is going to do a type mapping for us. And what we can do is we can pass in the type of a function and it'll give us the return type back. So let's say we've got a function here called build initial state, and you can see what it does is it returns an anonymous type. We're just making up an object on the fly with properties called is busy, last update, and errors. So let's say what I want to do is define a new type called state whose value is equal to the return type of that particular function. Okay, so that would be really tricky to do without map types, but here it's simple. So if we look at how that's implemented, this, I have to say, whenever I saw this for the first time, this completely threw me. Okay, but what we're doing here is we're saying, okay, if there's some type T where T extends any function, okay, so you see the arrow bit here. So we're saying, okay, if T extends from the class of functions that take something and return something, well, that's all functions. So effectively, we're saying if T is a function, then infer R, where R is the return type of the function. So very long story short, what we're saying here is if T is of the type of functions, then infer R, where R is the return type of this particular function. Yeah, so that's how we pass in the type of a function, and this evaluates to the function's return type. Which is very, very useful. Yeah. Another example, let's go back to our can activate function, which we saw earlier. So remember that returns a Boolean or a URL tree or a promise of one of those two or an observable of one of those two. So what we're saying here is, okay, there's some type T, yeah? And if T extends promise, in other words, if T is a promise, well, then what we want back is P type, the type of the thing in the promise, yeah? On the other hand, if T is some kind of observable, then what we want back is the thing in the observable. So you see there, for example, with result 3, if I was to say, okay, unwrap a promise of Boolean, then we would get back Boolean. Okay, so what we're doing here, if you like, is we're reaching into types and pulling back constituent bits. So we can say, here's a function, I want the first parameter or the last parameter or all the parameters or the return type, and all of this is being figured out on the fly at compile time. Yeah. So a practical example again of where this would be useful. Yeah, I'm sure you're all familiar with the three trees problem, as it's sometimes called, where you have a type and then you have the real version of the type, but then you have the version used in the UI and the version used in the database. So here we've got an interface to represent an employee, and we've nicely, strongly typed this. So you see there DOB and start date or dates, But let's say for the purpose of transferring data around in the UI, date won't work. We need string. So what we'd have to do without map types is we'd have to write these things as separate interfaces, and in our coding we'd have to keep them in sync. Okay, but what we can do with map types is we can do this here. So we can have a type mapping called date to string, where we're saying a date to string of employee is a new type, which is the same as employee, but every property which was of type date is now of type string. So what we're saying in that single line there inside the braces is we're saying, okay, iterate over all the properties, so for every property in the input type, we want a property in the output type. Yeah. But if a property in the input type, well, if it was of type date, well, then in the output type, the matching property should be of type string. On the other hand, if it wasn't of type date, leave it alone, just use the original type, whatever that was. And again, this comes down to the single source of truth. That's the Moazab's bit. That's the bit that makes it really cool. So instead of having to manage two versions of a type or three versions of a type, the real one, the GUI one, the database one, we can pick which one is going to be the real one, and then we can generate the other two from that. Very, very cool.
Awesome. Something else we can do is template literal types. And these are basically extending the literal types to support JavaScript and TypeScript templates. So this is basically extending that literal type concept to patterns of strings. And this can be combined with everything we've seen already to do some really interesting things. So the way that you do it is that in a location which requires a type, we put a template string. But the things that we embed in that string have to be further types. So we could, for example, create a type getter of t, where t will be some string. And what we'll get back is a new type that is get and then that name. There's actually some built-in functions like capitalize here to do transformations. Those you couldn't code this yourself. It has to be sort of built in, intrinsic in the language. So if I said, for example, getter of name, I would get back another type, get name, where name was capitalized. So we can use this when we're doing mapping to build out new keys in sort of really funky ways. So I've extended getter to getters, and that's a mapped type here. And what we're doing here is we're basically going through K in the type T, and then we're basically saying, well, don't use those keys, convert the key to a getter. Okay, so the keys that this type is going to produce will be get name, get age, get DOB, whatever the properties of the original T are. And then we're saying the type of that is going to be a function whose return type is the type of the original property. So it's basically creating us a type like the getters that we'd have in Java. The setters works exactly the same, only this time it's producing a function which takes an input of the type of the property T of K. And then what we can do is we can do an intersection to combine these two together into some type that we called Javify. Okay. And this is complicated stuff, but the key thing that I want you to take away is that in one line, we can say type employee Java is equal to Javify employee, and it would be equivalent to copying and pasting and writing out all of this code. So we remove all of this duplication, all of this noise, and we have a single source of truth. So if employee changes, the types change, the number of properties changes, employee Java will automatically update. That's the goal here. And we can actually do template literals types in discriminated unions as well. And something that's not in the language yet, but it is going to be in the next release in 4.5 is using sort of open template literal types in discriminated unions. So here, we're doing our keyboard touch mouse event example again, but now we're saying that the kind property of renamed to type, and now we're saying it's not just key or keyboard, it's key anything. A touch event is touch anything. A mouse event is mouse anything. Okay, any string can follow those that sort of prefix. And the compiler can still do comparison to those kinds of strings and figure out that it's a template or type and still discriminate down to a specific value. So here we're switching on the type again, but now I can have cases key down and key up, and both of those will narrow my event type down to a keyboard event. I'll get autocomplete for keyboard event. I'll get error checking for keyboard event. Mouse enter, mouse leave, touch start, touch end, these kinds of things. And it's all sort of done automatically. So this is definitely Momoa's abs.
Yep.
Other languages, Garth?
Yeah, very good. So kind of just as a finale, I noticed there's a question there asked in the chat. What other languages support structural typing? As far as I know, and Eamonn, you can correct me on this, TypeScript is the only one we're aware of at the moment. There are wonderful new languages. I have a shelf of shame on the bookshelf behind me there. So you've got like Julia, Rescript, formerly Reason, Elm. There's all kinds of things that I want to go out and learn. But as far as I know, TypeScript is the only language offering structural typing at the moment. Yeah.
Some of, I guess you could say like some of the functional languages, like the ML style languages, they have such extreme type inference.
Yes.
That it's pretty much equivalent. So you don't specify the types, but it all just largely works.
Yes.
Because it infers the types, I guess.
Well, which leads us nicely on to this here. So if you want to see like 15 minutes into the future, this book by Scott Voloshin is absolutely brilliant. It's all written in F#, and it shows how you can use algebraic types in F# to model the problem domain using domain-driven design. So normally your DDD, model would be fully OO. This is fully FP and F# with algebraic types. Absolutely stunning. Really, really good. So the features that we've been looking at in TypeScript are leaking into existing languages. They're slowly coming your way. Yeah. So 3 like single slide examples. Yeah. So first of all, here's one we did in Scala. So if you look at the top line there, we've got the type async result, and that's either a T or a future of T or a stream of T, so we're echoing back to that Angular example that we've already seen a couple of times. So future is the standard Scala future type. Stream is from FS2, which is the standard Scala streams library. And you see there, we can switch on the type, and it'll create variables of the appropriate type. So if it works out it's a stream, we'll have a variable called FS2 of type stream. Works out it's a future, variable called future. You get the idea. So it's not quite the power that you have in TypeScript, but close, And then in Python, I already knew that Python had type annotations. I didn't realize until we did this talk that it is a union type as well. So I can declare async result, and I can say that's either a string or a future or an observable. And then I can match in it as before, and I can do appropriate things. So because this is a dynamically typed language, we don't need to worry about the generics and the type parameters and so on, but that does bite you a little bit. Yeah. So the IDE can only give you so much help. So whenever you say result dot, you see all the operations of all the types in the union and so on. So it's not quite as rich as the help you get through Scala. Yeah. And then at Eamonn's insistence, I wrote PHP for the very first time for this talk. Thank you for that, Eamonn. I will get you back. Yeah. Shut up and eat your mush. Yeah. So you see here, we've got a function called handle result, and it takes a variable called result, which gets a sigil in front of it, because apparently that's what one does in PHP. And then you can see that result is either of type string or future or stream. Okay. And again, we can go out and work out the type and act appropriately and so on. So the point we're just making there very quickly in those last 3 slides is that these features, in TypeScript are slowly making their way into the other languages that you use all the time. Okay. So just to finish off by returning to our central point, this is not just for the Haskell and the category theory, and the F# and the Scala community and so on. This is practical and useful to everybody. And to begin with, you'll start out using the type wizardry that other people have done for you. Yeah. But bit by bit, as happened to us, you'll get seduced, you'll get dragged in, you'll start, you won't be afraid of it anymore, and you'll start saying, oh, how does that actually work underneath the hood? And once you understand what it's doing, then you'll be able to go out and apply it for yourselves, and you'll be able to use it for good, not evil, So it is very, very powerful. Yeah. And that's our show.